Dear students, welcome back to the lecture series on solid state. In this session, we will continue our discussion on the laws of crystallography. And today, we will see a few more terms related to crystallography, namely crystallographic axis and axial angles. We will see what is meant by a unit plane, axial ratio, elements of the crystal, followed by a detailed discussion on the next law of crystallography, that is the law of rational indices. In the previous class, we discussed the two laws of crystallography, the law of constancy of interfacial angles, which states that the angle between the corresponding crystal faces remains the same for a given substance, no matter how the faces develop, and it is also known as Steno's law. And the next law was the law of symmetry, which states all crystals of the same substance possesses the same elements of symmetry. Before moving on to today's session, let's discuss the assignment questions of the previous class. The first question was, according to the laws of crystallography, what remains constant for the crystals of a substance? We have option A, the number of faces, option B, the size of faces, and option C, the angle at which the two adjacent faces intersect. And we have seen that according to the law of constancy of interfacial angles, the angle between the two adjacent faces or the angle at which the two adjacent faces intersect will remain constant. So, the correct option is option C, that is the angle at which the two adjacent faces intersect will remain constant. Second question, which of the following symmetry element is denoted by Cn? In the last class, we discussed about various elements of symmetry possessed by a crystal. We have the mirror planes, that is an imaginary plane that cuts the crystal into two equal halves such that one is the mirror image of the other. And option B, you can see a group of proper rotational symmetry. Option C, an inversion center. Option D, identity. So, all these are elements of symmetry. So, option B, that is a group of proper rotational symmetry, is denoted by the symbol Cn. If the rotation is through 360 degree, then this is denoted as C1. If it is through 180 degree, then it is a C2 axis. So, similarly, in general, we can represent a rotational symmetry, proper rotation axis as Cn. Okay. So, the correct answer is option B, a group of proper rotational symmetry. The third question, the elements of symmetry in a crystal are, we have option A, plane of symmetry, option B, axis of symmetry, option C, center of symmetry, and option D, all of the above. And in the last class, we saw different elements of symmetry. A crystal possesses a plane of symmetry. It also possesses a proper rotation axis or axis of symmetry. It also has a center of symmetry. Okay. And what is a center of symmetry? It is a point within a crystal such that when we draw a line through that point, it touches the surface of the crystal at equivalent positions in both directions. Okay. So, that is called a center of symmetry. So, A crystal possesses a plane of symmetry, an axis of symmetry and a center of symmetry. So, the correct option is option D, all of the above. Fourth question, list the elements of symmetry for a perfect cube. In the previous class, we have seen that a cubic crystal possesses a total of 23 elements of symmetry. The 23 elements of symmetry are listed below. A cube possesses one center of inversion or a center of symmetry at the center of the cube. It has 3 four-fold rotation axes, or we may say it has 3 C4 axes. 4 three-fold rotation axis, that is 4 C3 axis. It also has 6 two-fold rotation axis, that is 6 C2 axis. 3 rectangular planes of symmetry and 6 diagonal planes of symmetry. So, in total, a cube possesses 23 elements of symmetry. And the last question, why a 5-fold or 7-fold rotation axis is not possible in true crystals? And this is due to the constraints of the space filling in 3 dimensions. We have seen that for a proper rotation axis, only a certain set such as a C1, C2, C3, C4, C6, etc. are possible, but we cannot see a C5 or C7 rotation axis. It is because a 5-fold or 7-fold symmetry cannot repeat periodically to fill space, making them impossible in true crystals. And this restriction of the 5-fold or 7-fold symmetry is also known as crystallographic restriction theorem. And now we will move on to today's session. We will see a few more important terms related to crystallography. In the last class, we have seen that the flat bounding surfaces of a crystal are called its faces. Now, let us draw a crystal. Let us consider a cubic crystal. So, when we consider a cube, the flat surfaces, that is, let us see the faces. The front part, we have this face 1, and on the back we have face 2 on the back side. Now, on the sides, this is one face and this is another face. Now, the next face is one on top and one on bottom. So, in total there are 6 faces for a cube. So, such flat bounding surfaces are called faces. Now, when we consider the crystal as a whole, that can be regarded as made up of a set of parallel and equidistant planes parallel to the crystal faces and passing through its structural units. Now, what are the structural units? It can be atoms, ions or molecules. So, a plane passing through the structural units and parallel to the crystal faces. Such planes are called crystal planes or lattice planes. the term lattice is a mathematical concept which denotes a periodic array of points, and the points are arranged in a particular geometrical pattern. So, that array is called a lattice. And we will discuss more about lattice points and lattice planes in the later classes. So, for the time being, let us consider the term crystal planes only. Okay. So, what is meant by a crystal plane? It is a plane that is made up of parallel and equidistant, parallel to the crystal faces and passing through the structural units. Let us see some examples for crystal planes. Okay. So, in figure A, we can see this shaded portion. So, this is a cubic crystal, and if we consider this area, this shaded portion represents a plane, and this plane, you can see that it is parallel to the z axis, parallel to the y axis, but it cuts the x axis. Okay. So, and if we consider a cube, it will have particles at the corners. So, just imagine that the particles are present at the corners. So, you can see that this plane is passing through these particles, okay, through these structural units. So, that is called a crystal plane, and another word for crystal plane is lattice plane. Okay. Now, figure B and figure C also represents another kind of crystal planes. In figure C, you can see that this area, okay, so this shaded region represents a plane, and you can see that this plane cuts all the three crystallographic axes, that is x, y and z. Okay. So, like that we have different kinds of crystal planes. And now, in order to define the geometrical form of a crystal, we generally need three coordinate axes. Okay. So, such coordinate axes are generally represented as x, y and z, and this x, y and z axes are generally called the crystallographic axis. So, the crystallographic axes are imaginary lines that we can draw within the crystal lattice. So, as you can see in this figure, this is a cubic crystal and there is a plane. So, in order to define this, we need three axes represented as x, y and z. Now, these three crystallographic axes or the lines, they meet at a common point at origin O. So, the lines we have OX, OY and OZ, the three crystallographic axes. Okay. So, these three axes will define a coordinate system within the crystal. So, the crystallographic axes are imaginary lines that we can draw within the crystal lattice in order to define a crystal structure. These crystallographic axes are chosen in such a way that all the crystal faces and planes will either intercept one or more of these axes at definite distances from the origin, or it can be parallel to one or two of them. So, if we consider again this figure, we have the three crystallographic axes x, y and z, and this is the plane. Okay. Let the plane be represented as ABC, okay, ABC plane, and these axis lines meet at the origin O. So, you can see that the crystallographic axis and the plane cuts the crystallographic axis, all the three axes, that is the x, y and z axis. So, we can choose an axis in such a way that all the crystal faces or planes will either intercept at one or two of these axes, or it can also go parallel. In this figure, you can see that the plane cuts all the three axes. Now, if you consider another plane, if you consider this front plane, okay. So, in this shaded portion, you can see that this plane is parallel to the z axis, parallel to the y axis, but it cuts the x axis, okay. So, it is either it cuts one or more of the axis, or it can also be parallel to one or two of them, okay. Now, usually when we choose a crystallographic axis, three mutually perpendicular axes are chosen. But maybe due to some geometrical constraints, instead of three mutually perpendicular axes, they may incline at particular angles. So, such angles are called axial angles. So, this is a cube and we have the three crystallographic axes x, y and z, okay. So, the angle between the y and the z axis, okay. So, the angle between y and z axis is denoted as alpha, and the angle between the x and z axis is denoted as beta, and the angle between x and y axis is denoted as gamma, okay. So, these three angles, that is alpha, beta and gamma, are together known as the axial angles. So, we have seen what is meant by a crystallographic axis and how the crystallographic axis intercepts the plane, and the angle between these three axes are known as axial angles, generally represented as alpha, beta and gamma. Now, let us see what is meant by a unit plane. A particular plane of the crystal which cuts the crystallographic axis can be chosen, in terms of which the crystal faces may be described. Such a plane is called a standard plane or unit plane. If we consider this crystal again, we can see that the plane cuts the three crystallographic axes. So, we can take this plane, or we can consider this plane as a unit plane or standard plane. So, let me denote this plane as A, B and C. So, we have a unit plane here denoted as A, B, C. Now, if we consider the distance from the origin O to A, that is OA, and that denotes a distance at which the plane cuts the crystallographic axis. So, let me denote it as small a, okay. The distance OA is small a. Similarly, the distance OB can be represented as B, that is OB equals B, and the distance OC can be represented as C, that is OC equals C. So, these distances, that is A, B and C are called the unit intercepts. Okay. So, we have seen what is meant by a unit plane and what are unit intercepts. Okay. So, a unit plane is also known as a standard plane, and it is a particular plane which cuts all the crystallographic axis. Okay. And that is described in terms of the unit intercepts. And what are unit intercepts? It is the distance from the origin to which the plane cuts the crystallographic axis, and they are generally denoted as A, B and C. Now, next term is axial ratio. Again, when we consider the same plane, we have seen the unit plane A, B, C, and we have also seen the unit intercepts represented by small a, b and c, which are called the unit intercepts. Now, the ratio of these intercepts made by the unit plane on the crystallographic axis is called the axial ratio. That is, A is to B is to C. The ratio of the unit intercepts is called axial ratio. Now, while we stating an axial ratio, B is conventionally made unity. That is, we can say A by B is to 1 is to C by B. For example, in K2SO4 crystal, potassium sulphate crystal, the axial ratio A is to B is to C is given by 0.5727 is to 1 is to 0.7418. Now, next is the elements of the crystal. Till now, we have seen about the three crystallographic axes, a unit plane, how a unit plane intercepts at the crystallographic axis, and that intercepts are given as the unit intercepts given by A, B and C. We also see the axial angles, that is alpha, beta and gamma. So, these two together are known as the elements of the crystal. Okay. So, the elements of a crystal is described in terms of the axial ratios, that is A is to B is to C, and the axial angles. Now, we will move on to the law of rational indices. It states that the intercepts of any plane of a crystal along the crystallographic axis are either equal to the unit intercepts or some simple rational number multiples of them. We have seen how a plane intercepts at the crystallographic axis. Now, according to this law, the intercepts of any plane of a crystal, it cuts the crystallographic axis equal to the unit intercepts, or it may be some simple rational number multiples of them. And the ratio of the intercepts of any crystal plane on the crystallographic axis is given by PA is to QB is to RC. Now, let us make it more clear by drawing a plane. So, first let us draw the crystallographic axis. So, we have the x, y and the z axis. So, consider a plane So, let the plane be denoted as PQR, and we can draw a unit plane here. So, let it be A, B and C. Okay. So, in this figure we have a plane PQR and we have considered a unit plane ABC in this figure. Now, let us mark the intercepts. That is, at OA the intercept is A, at OB the intercept is B, and at OC the intercept is C. Okay. Now, what will be the axial ratio? That will be A is to B is to C. Now, according to the law of rational indices, the ratio of intercepts of any crystal plane on the crystallographic axis is given by PA is to QB is to RC, where A, B and C are the unit intercepts and the coefficients P, Q and R are called the Weiss coefficients or Weiss indices. And this is a very important term, the Weiss coefficients or Weiss indices. So, these Weiss indices are a way to express the location of a crystal face in relation to the crystal axis. So, these Weiss coefficients may either be equal to unity, that is the value of P, Q and R can either be equal to unity, or it can be fractions, or it can be whole numbers. Okay. This Weiss coefficients or Weiss indices, as I said earlier, need not always be simple whole numbers. They can also be infinity or fractions. For example, if a plane makes intercepts 2B and 3C respectively on OY and OZ, but goes parallel to OX. So, let us determine the coefficients. It is given that on the OY axis, it makes an intercept of 2B. On OZ, it makes an intercept of 3C. But it is given that it does not cut the OX or the x axis, it goes parallel to OX. It goes parallel to OX means it does not cut the x axis at all. So, it will be infinity A, where A is the unit intercept and the coefficient will be infinity. So, what will be the Weiss indices or Weiss coefficients? The Weiss indices are given as infinity, 2, 3. It's corresponding to the OX, OY and OZ. Okay. So, the Weiss coefficients or Weiss indices need not always be whole numbers. It can be fractions or it can also be infinity. Weiss indices provide a way to describe the position of a crystal face by quantifying how far the face cuts into the crystal's main axis. And Weiss indices are a fundamental tool in crystallography for characterizing crystal shapes and orientations. So, coming back to the law of rational indices, it is an empirical law in crystallography, and this law was proposed by R.J. Hay in 1784. It is based on the observation that the natural faces of a crystal are built by stacking of their elementary blocks like cubes or rhombohedrons. Okay, that is the basic building block, or the elementary block can be cubes or rhombohedrons. When they are stacked together, they are stacked together in a particular pattern. Okay, so, based on that observation, he proposed the law of rational indices. He also discovered that the crystals always cleave along specific planes, and that planes are now known as the crystallographic planes or crystal planes. And due to his remarkable contributions to the field of crystallography, R.J. Hay is also known as the father of modern crystallography. Now, let us see some more examples related to Weiss indices. Determine the Weiss indices for a plane when the intercepts along the axis are 2a, 3b and 2c. And on the second question, a minus 2b and 3c. First, let us answer the first question. It is given as 2a, 3b and 2c. We have the intercepts a, b and c. And what are Weiss indices? Weiss indices are given by PA is to QB is to RC, and these coefficients P, Q and R are called the Weiss indices or Weiss coefficients. So, in this question it is 2A, 3B and 2C. So, what will be P, Q and R? So, P is 2, Q is 3 and R is 2. So, the Weiss indices will be 2, 3, 2. Now, let us see the second question. In the second question, the given intercepts are A minus 2B, 3C. So, again when we consider the P, Q, R, the coefficients, the coefficient of A is unity, that is 1, the coefficient of B is minus 2 and the coefficient of C is 3. So, we can say the Weiss indices as 1, 2, minus 2 and 3. Now, you might be thinking why there is a minus sign over here, and we know that the Weiss indices are coefficients of the unit intercepts, and these intercepts can be at negative values also. For example, if we consider a graph, okay, let me mark the points. Okay. Now, suppose the graph is like this. If we extrapolate the graph to find out the intercept, we can see that it extrapolates like this and it touches the point minus 1. So, the intercept here will be minus 1. Okay. So, the Weiss coefficient can also be negative numbers. So, that is 1, minus 2 and 3. Now, another question. A face makes intercepts 2a and 3b on the x-axis and y-axis respectively and does not cut the z-axis at all. What are the Weiss indices of the face? So, it is given that the face cuts the x-axis at a distance 2a. It cuts the y-axis at a distance 3b, but it is given that it does not cut the z-axis at all. It does not cut the z-axis means it goes parallel to the z-axis. Parallel to the z-axis means the intercepts will never touch the z-axis, so that can be treated as infinity. So, the coefficient is infinity. So, we have on the x 2a, y 3b, it does not cut the z-axis or it is parallel to the z-axis. So, the coefficient of c will be infinity. So, what will be the Weiss indices? Weiss indices are nothing but the coefficients of the intercepts. So, that will be 2, 3 and infinity. So, these are a few problems based on Weiss indices or how to determine the Weiss coefficients or Weiss indices. So, in this session, we had a detailed discussion on the laws of crystallography. We saw the 3 fundamental laws of crystallography, namely the law of constancy of interfacial angles, the law of symmetry and the law of rational indices. And what is the law of rational indices? It states that the ratio of the intercepts on any plane that cuts the crystallographic axis, that ratio of intercepts will either be equal to unit intercepts or some simple rational number multiples of them. Okay. And while discussing this law of rational indices, we also see about the Weiss coefficients or Weiss indices, and they are the coefficients of the intercepts, generally denoted as P, Q and R. Okay. And that define a plane and the intercepts that it makes on the crystallographic axis. In the next class, we will see a detailed discussion on the internal structure of the crystals. Thank you.